Another technique of regularization is batch normalization. The problem that batch normalization solves is this. The problem is that in deep learning, the distribution of each layer's input changes during training. And the solution that batch normalization proposes is to fix the distribution. And interestingly, batch normalization, this technique of fixing the distribution, is a key solution to avoid or minimize the vanishing gradient problem. Now imagine, let's say this is my layer L1 and here's my layer L1, and let's say the output feeds to the next layer, let's say another layer L2, right? So the numbers, all the values that come out of this layer L1 may follow a certain distribution. Let's say the distribution shown by the blue line, or maybe the distribution shown by this red line, and so on. During training, it is possible that as we add more and more layers, layer L3, L4, L5, and so on, the distribution may start shifting to one direction or the other. Maybe at the beginning, in the initial layers, the distribution is in the center, but then as we do more and more multiplications, the distribution may shift towards the bottom, towards the upper range, such that gradually you only have a very few numbers with higher values, and then everything else is almost close to zero. So this shift in distribution is one of the biggest problems why we cannot train deep neural networks. And what batch normalization does is, if we add batch normalization maybe to the output of any layer, it simply shifts the distribution such that the distribution either centers around a particular value, or maybe the entire distribution remains centered, and so on. Adding batch normalization layers is very easy. Say we have a neural network model, let's say a convolutional neural network model with first convolutional layer and second convolutional layer, then all we have to do is add a batch normalization layer between any two layers that we want. And then it simply normalizes or batch normalizes fixes the distribution of the previous layer before it gets sent to the next layer. One of the problems with batch normalization is that it slows down the training. But otherwise, batch norm is a key to train really deep neural network models. To summarize the key ideas in regularization, what we want to do is start with an augmented input. I mean, if you can collect more data, that's good, but otherwise, start with augmented input and then use batch normalization in between your layers. Also use dropout in between your layers. If you want to use both, we can actually use batch norm and dropout alternatively. So maybe start with batch norm and then dropout, and then maybe batch norm and then maybe dropout again, and so on. And also we want to remember to do the training with callbacks. So then to summarize, when we want to train a very deep convolutional neural network or a very deep neural network, what are the villains, right? Say we start with an example. Let's say we want to create a convolutional neural network model that's very, very deep. So we start with model sequential and add one conv2d layers with 16 filters. And in a for loop, I'm going to add a conv2d layer with 4 filters, but actually 1,000 of them. So 1,000 layer conv2d layers. So obviously, if you train this model, your results will be terrible. Your model will take very long, first of all, and even if you get past the first few epochs, your accuracy is not going to look very good. And the major reasons, to summarize, is the major reasons or the major villains why we cannot train this very deep neural network is one is the vanishing gradient problem. That is the problem in which the output of the previous conv2d layer and the subsequent conv2d layers gradually become 0. So maybe the first number is 0.08, the second number becomes 0.0009, and so on, and gradually they underflow. The next problem is exploding gradient. That is, your numbers start becoming so large that either everything becomes 1 or everything becomes much bigger values. Another problem is the internal covariate shift. That is the distribution of the values that come out of your convolutional layer. At the beginning, maybe like a normal distribution and maybe look very good, but then gradually they start shifting such that in the subsequent layers towards the end, your distribution looks very skewed, and the distribution shifts such that the subsequent layers towards the bottom cannot accept anything reasonable. And using ReLU activation and using batch normalization greatly resolve these issues. But something to keep in mind is that batch normalization slows down training. So there is also, it doesn't mean that we can still have models with hundreds and hundreds of thousands of layers, but we can at least do a few hundred layers pretty easily with GPUs and other resources.